All right, let's dive right into this. Because today, we are going to completely shatter a fundamental assumption you probably have about how the world around you actually works. You know, most of us just go through our entire lives accepting gravity as the simple, undeniable truth of the universe, right? It's the invisible glue that holds the whole shebang together. But what if I told you that the way you were taught gravity works is actually, well, fundamentally incorrect? Welcome to today's Explainer, where we're going to unravel the true nature of reality, space, and time, completely guided by the mind-bending discoveries of Albert Einstein.
So, why does an apple fall to the ground? I mean, it seems incredibly basic, but let's push that a little further. Why does the moon stay perfectly in orbit around the Earth instead of just flying off into the dark void? And here's the real head scratcher for you. Why does light, which has absolutely zero mass, bend when it passes near a black hole? For over 200 years, the greatest scientific minds on the planet firmly believed they knew the exact answer to all of these questions. They thought they had the universe completely figured out, but man, they were about to get the rug pulled right out from under them. Chapter 1. Newton's Unsolved Mystery. To understand just how massively Einstein disrupted the scientific world, we actually have to go back to 1687 and meet Isaac Newton, a genuinely brilliant thinker who gave us the law of universal gravitation, which provided this elegant mathematical framework that seemingly answered, well, everything. And what's truly astonishing is just how much Newton's singular theory accomplished. His law basically stated that every single object in the universe attracts every other object. If it has mass, it pulls. The larger the mass, the stronger the pull. The farther apart they are, the weaker the pull. It was elegant, and more importantly, it worked. It flawlessly explained falling apples, the complex motion of the planets, the predictable rhythm of ocean tides, and even the paths of passing comets. It was, without a doubt, one of the most successful theories in human history. But here's the massive, glaring problem. A literal 200-year cold case that absolutely haunted physics. Newton could calculate exactly how much gravity would pull an object, but he had absolutely no idea how it was doing it. I mean, how does an invisible force pull two completely disconnected objects across millions of miles of empty, dead space? Newton himself admitted this was absurd. He famously confessed that the cause of this power was completely beyond his understanding. Chapter 2. Gravity is just geometry. So that mystery sat entirely unsolved until 1915, when Albert Einstein stepped onto the scene with a complete paradigm shift. He proposed an idea so profoundly radical, so breathtakingly weird, that it completely rewrote our understanding of existence. So the crucial point here is that we have to completely shift our perspective. Newton envisioned an invisible pulling force, kind of acting like a cosmic tractor beam between objects. But Einstein revealed a completely different reality. Gravity isn't a force at all. It is the curved geometry of spacetime. There is no magical pulling force. Instead, gravity is quite literally just the shape of the universe itself. To really grasp this, we have to understand what Einstein meant by spacetime. He realized that space and time are not two separate things. They're inextricably woven together into a single, invisible, four-dimensional fabric. And here is where the magic happens. Every object with mass bends this fabric. The more massive the object, like a star or a planet, the deeper it curves the spacetime around it. Which means, right now, the Earth is not being pulled by the sun's gravity. Not at all. The Earth is simply rolling along the natural, curved path that the sun's massive weight has carved into the fabric of spacetime. Let's ground this with a classic, incredibly helpful visual. Imagine a large trampoline stretched out super tight. That's spacetime. Step 1. Place a heavy bowling ball right in the middle. The fabric of the trampoline obviously sags and bends under its weight. Okay, step 2 is complete. Now for step 3. Take a small marble and roll it sideways across the trampoline. It doesn't travel in a straight line, does it? Nope, it spirals around the bowling ball. The bowling ball isn't reaching out and pulling the marble with some magical force. The marble is simply following the curved surface that the bowling ball created. Now, as an explainer, I do have to note the limits of this analogy, because the trampoline itself relies on Earth's gravity pointing down, but it brilliantly captures the visual intuition of how our solar system actually works. Chapter 3. Bending light in time. Now, proposing a beautiful theory is one thing, but proving it, that's another entirely. And Einstein's predictions based on this geometric universe completely shocked the scientific community. Quite frankly, they sounded purely like science fiction at the time. I want you to think about this question for a second. Under Newton's old rules, a pulling force only works if an object has mass. So How on earth could gravity affect a beam of light, which has absolutely zero rest mass? Under Newtonian physics, it simply shouldn't. Light should always travel in a perfectly straight line, completely ignoring gravity. And this brilliantly illustrates the genius of Einstein. In his universe, light actually is traveling in the straightest possible path. It's just that the space it's traveling through is curved. When spacetime bends around a massive star, the path of the light bends right along with it. And in 1919, during a total solar eclipse, astronomers finally tested this. They measured the position of starlight passing near our sun. And sure enough, the light bent exactly as Einstein predicted. It was a massive confirmation that made Einstein a household name literally overnight. But the weirdness absolutely does not stop with light. Because space and time are connected, bending space means you are also bending time itself. This leads us to what's called gravitational time dilation. The stronger the gravity or the deeper the curve in space-time, the slower time actually passes relative to someone further away. I know, this sounds insane, but it is a measured, confirmed fact of our reality. The GPS satellites currently orbiting the Earth, the ones powering the maps on your phone, they actually experience time slightly faster than we do on the ground because they are in weaker gravity. If scientists didn't program those satellites to correct for Einstein's relativity, your phone's GPS would fail by miles within a single day. Chapter 4, Black Holes and Ripples. All right, let's take this geometry to its absolute extremes, leaving our cozy solar system behind for the deep cosmos, where space-time does things that completely defy everyday logic. So when a supermassive star collapses in on itself, it creates a curve in space-time so infinitely deep that it essentially becomes a bottomless pit. We call this a black hole. Now, it is absolutely vital to understand that a black hole is not a giant cosmic vacuum cleaner actively sucking things in. It's simply a region of extreme geometry. The slope of space-time is so impossibly steep there that the escape velocity required to climb out of the curve is faster than the speed of light. And since nothing is faster than light, nothing can get out. Near a black hole, time slows down so drastically that if you were to hover near one, thousands of years could pass on Earth while you only experience a few hours. And think about this. If space-time is a fabric, that means it can ripple. Einstein predicted that when incredibly massive objects accelerate, like two black holes violently spiraling toward each other, they would create literal waves in the fabric of reality, traveling outward at the speed of light. For a century, this was just a mathematical theory. But in 2015, in one of the greatest scientific triumphs in human history, scientists actually detected these exact ripples for the very first time. These waves originated from two immense black holes colliding over 1 billion light-years away, washing over our planet and gently stretching and squeezing our entire world by a fraction of an atom. I mean, how incredible is that? Let's move to this timeline and see how this all builds, because looking at it really puts this epic journey into perspective. For over 2 centuries, we lived in Newton's universe, successfully mapping the stars, but completely blind to the underlying machinery. Then, in 1915, Einstein gave us the literal blueprints to reality. By 1919, we saw light bend, confirming the geometry. And nearly a century later, in 2015, our technology finally caught up to Einstein's math, allowing us to literally hear the gravitational waves of colliding black holes. It evolved from an unsolved mystery into one of the most successful, rigorously tested scientific frameworks ever conceived by humanity. Chapter 5, Your New Reality. Okay, let's bring the vastness of the cosmos back down to Earth for a second, right into your living room. Because understanding general relativity isn't just about black holes and distant galaxies. It completely changes how you should perceive every single physical interaction you have with the world around you today. The next time your phone slips from your hand and crashes to the floor, and let's be honest, it happens to all of us, I want you to remember this explainer. The phone is not being pulled by some magnetic-like force from the center of the Earth. There is no invisible string. What's actually happening is that the mass of the Earth is warping the space and time around you. Your phone is simply trying to travel in a straight line, but the reality it exists in is curved downwards. It is tracing the shape of the universe itself, straight to your floor. Gravity is not a force. It is geometry. It is a universe vastly more wondrous and, frankly, bizarre than we ever imagined. So as we wrap up this mind-bending journey, I want to leave you with a question to consider. With this completely new understanding of curved space and dilating time, if you had a ship that could survive the journey, where would you go first?
Would you just want to see the curve of Earth from orbit, visit the massive dent our sun makes in space-time, witness the time-bending extreme of a black hole, or cross the vast waves of another galaxy? Think about it. Drop your thoughts on that and keep exploring this incredible universe we find ourselves in. Until next time, keep learning and keep looking up.